All right. Just a forewarning before I begin, I'm still a little behind on emails. In fact, I think that's my goal today, is to find some time to sort of lock myself in my office and say I'm just going to respond to emails today. So my apologies if you've sent me something and I haven't yet responded yet. Okay, so let's get started. My TAs are still sort of working on chipping away at the outstanding homeworks that need to be graded. So homeworks 3.1 to 3.2 have been graded. 3.3 to 3.4 are being graded, but all the solutions are posted for those assignments. 3.5 is assigned today, or is due today, and then 3.6 is assigned today and it's due Wednesday. Just so everybody is aware on the schedule moving forward, it's not going to happen, within the next couple of days. But we are going to, at some point, have celebration number 2, just so everybody is aware. So we're currently, I guess we could say we're on homework assignment 3.6, since it's going to be assigned today. We'll have a homework 3.7, 4.1, 4.2, and 4.3. 4.3 is a little bit of a longer assignment, and there's not really anything I can do about that just because of the nature of the problem. So 4.3 is going to be one of those assignments that I don't remember the day, but it's not going to be due the following lecture. It'll be due the lecture after that, just because it's going to take a little while to do it. And then we'll have our second celebration after homework 4.3. So we're still rocking and rolling in the class. We're well on schedule and whatnot. Before and one more thing, I do have the attendance grades and whatnot posted to Blackboard. Any questions on that? Okay. Now, in terms of, there is one thing I did want to mention. Is anybody planning on going to the Career Expo on Wednesday? I'm just curious. Good. Did anybody not know about the Career Expo on Wednesday? Okay, good. I'm glad I'm talking about this. So Wednesday, October 5th, we are having our regular Marshall University Career Expo. I think there's something like 38 companies that's going to be there that's focused on engineering students. So that's a lot. I don't know about you. I like money. I have a feeling you do too. There's definitely opportunities for co-ops, internships, so on and so forth. If you're going to go, I would have a professionally polished resume. Have that ready. If some of you, how many of you are in 217 right now? I'm just curious. Some of you already have that because, or I would think by now, because I think that's one of the first things that you've done in that class, right? You just got it done. Yeah, so good. If you're going to go to the Career Expo, I would dress somewhat formally, unless it is absolutely unavoidable. I would dress formally. I don't think you need to wear the full suit and tie or full shebang, but business casual or professional would be required. Again, they're looking for employees. So you're looking for employers. It's a match made in heaven. So, okay. Any questions? All right. So just want to make sure that you're aware of that. Okay. Let's get into the land of statics. And I would argue that we've been dancing around this topic in here for a few lectures, and it's high time we actually started talking about it. And so our concept, or our lecture today, is on equivalent systems in 2D. And so I mentioned this analogy last time, but just to recap, in our first real unit of the class, when we were discussing forces and statics of particles, we sort of handled it in 3 phases. The first step was to just learn how to describe forces, the IJK notation, or graphically or trigonometrically, but ultimately just how to describe forces. And then we started asking how to add those forces up to determine resultants. And then the third step is static equilibrium. What are the unknown forces necessary to keep a particle in equilibrium? Well, we're sort of doing the exact same thing. We're doing the exact same thing for rigid bodies. And so the first phase, which I would argue is done now, is learning how to describe moments. Okay? And we had all sorts of special cases with moments in 2D, force couples, moments about an axis. But ultimately, that's what that whole process was about, was the description of moments. Now we're in phase 2, which is how to add those systems up. So ultimately, our goal is to look at equivalent systems. And I mentioned equivalent systems last time, but I want to be clear about that today, because literally our entire lecture is going to be focused on one example. And so you'll see what I mean as we delve into this. So I give you a rigid body or some system that is subjected to a bunch of forces. And that happens all the time in the land of engineering. And in engineering and in mechanics, it is often easy and it is often advantageous to take this system with a bunch of forces and collapse it into a smaller, more manageable number of forces. And we're going to have some very real examples of that later when we look at some topics in structural analysis and what have you. You're going to find some very important applications of this. So what we then do is we identify a new term, which is what I'm calling two systems of forces which are equivalent. And I would say that we've kind of danced around this term already. If I have a particle with, say, 4 loads on it, and I add those forces up and I get a resultant, what I'm saying is I could take those 4 loads and replace it with this one resultant, and those two systems are equivalent. Well, a more general definition of that would mean that two systems are equivalent from a statics perspective if the sum of forces in system 1 equals the sum of forces in system 2, and the sum of moments in system 1 equals the sum of moments in system 2. So now we have to consider both sum of forces and sum of moments. So with every force on the system, we have just the force, and then we have to ask how much moment it is generating about a point in question. Now, I want to be clear, we are not yet dealing with static equilibrium. So static equilibrium would be saying, okay, let's take the sum of forces, set it equal to 0. Let's take the sum of moments and set it equal to 0 and solve for unknowns. Right now, we're not doing that. We don't have any unknowns on the system that we're having to solve for. We're going to do that later. That's what, when we start getting into homework 4.1, 4.2, that's what we're going to be doing there, is solving for the unknowns required to achieve static equilibrium. Right now, we're just taking our system of forces and collapsing them into a more manageable number of vectors. That's all we're doing today. Does that make sense? Okay, so here's what we've got. Okay, so I've got this barge here out in the river, and I've got 4 tugboats that are each pushing on this barge with a force of 5,000 pounds. So this one's pushing with 5,000 pounds, this one's pushing with 5,000, 5,000, 5,000. What I want to do is I want to take these barges and I want to collapse them into a more manageable number of vectors. Specifically, what I'm going to first do is I'm going to collapse it into a system of 2 vectors. That vector being a force coupled system. So basically, these 4 vectors are going to become 2 vectors, 1 force and 1 moment. Okay. Then the second question is, where should a single, more powerful tugboat push the cruise ship to produce the same effect? That one going to take a little bit of discussion. But the long story short is, this is system 1 with 4 vectors. We're going to take system 1, turn it into system 2 with 2 vectors. And then after that, we're going to take system 2 and turn it into system 3 with 1 vector. So we're going to take this and sort of reduce it more and more and more. Now, our point of interest for this problem is this point 0 or point naught. That's going to be our reference point here on this problem. Now, one thing that I will mention now, just to give you a taste of things to come later, some of you might be thinking, well, why that point? What's so special about this particular point on the barge? And granted, for what I'm about to say, where this point is in a little bit of an odd spot. But one of the things we're going to learn about starting in Module 5, or when we start having the homework 5.1, 5.2, is we're going to learn about centers of gravity and centroids. And so maybe what we're interested in is determining the response or the system of forces and how it affects the system with reference to the centroid, and so, or the center of gravity. You probably understand what center of gravity means. Centroid is just sort of a generalized form of that, but we'll get to that later. Okay. All right. So let's get into the land of equivalent force systems. Let me make this a little bit bigger. All right. So we have four forces, four tugboats being applied to this system, and conveniently, they have already been numbered for us. They've already been named, and I kind of like this this naming system. It's going to make it a little easier to reference. Now, one thing I'm going to go ahead and do right now is introduce some units considerations in this problem. Okay. Now, in general, if you think about moments, you can think about them as forces times distances, right? Because that's ultimately what you're doing, like R cross F or FD, it's forces times distances. Okay, my force is something like 5,000 pounds, and then my distances are going to be something like 100 feet, 300 feet, 200 feet. So if I start taking 5,000 pounds and start multiplying them by these distances, bless you, these numbers they're just going to get big, right? They're just going to get large. And honestly, I'd like to make my numbers a little bit more manageable. So what I'm going to do is I'm going to introduce two terms here at the top just to make life a little easier. Okay, first off, does anybody remember what I can do with 1,000 pounds in terms of units? There's a name for, if I take 1,000 pounds, I can call that one what? Kip. So what I'm going to do is I'm going to treat all the tugboats to have a magnitude of 5 kips as opposed to 5,000 pounds, just to make the math a little bit more manageable because the forces are kind of big. And to be clear, in civil engineering and even in some disciplines in mechanical engineering, I mean, you really can get some really heavy loads on the system. So it's actually advantageous to take the numbers and maybe make them a little bit more manageable. So kips was going to make our life a little easier. The other thing I'm going to make sure that everybody's aware of, because keep in mind what we're doing today is limiting our math to systems in 2 dimensions. We'll look at 3 dimensions during the next lecture. But remember, for moments in 2D, I do want to make sure that we have that sort of in our tool belt, that RxFy minus RYFX will yield a moment in 2 dimensions. Because ultimately we've got 1, 2, 3, 4 moments that we're going to have to compute. Okay. Now, what we're going to do here in this problem is there's a lot of vector description. And it's a lot of the same thing over and over again. So I do want you to be aware of that we're going to be doing sort of the same thing over and over and over and over again. So please bear with me on that. Okay? Now, so what I'm going to be doing in this problem is this. So let's read the 2 bullets that we've got to solve for. So the first bullet says determine the equivalent force couple system at point naught. So what that basically means is that I'm taking these 4 forces and I'm replacing them with a single force vector and a single moment vector. So the way that's going to work is to replace it with a single force vector, I'm just going to take each of these vectors and add them up, right? And then to replace it with a single moment vector, I'm just going to take R cross F for each of these vectors and add them up. So there's a lot of vector description that we need to do. So we're going to start off describing the force vectors, okay? So let's start off with that. So maybe what I'll do is I'll say write individual force vector in IJ notation. And note that if we were doing this in 3 dimensions, we would write it in IJK notation. So we're not dealing in 3D, so we don't have to worry about that. Let's start off with F1, okay? Okay, all right. So F1 is going to be this force right here, okay, this force right here. So we're going to have some pile of junk times I plus some pile of junk times J. Now note, here off to the side, that the magnitude of each of these vectors is 5 kips. Keep that in mind. All right. Now we've got 60 degrees for F1, so we're looking at this force right here, and it's pointing this way, okay? So let's be clear on that. This is a tugboat pushing on the boat, or on the barge. So the force is applied like that. So it is pointing to the right and down, right? So that means the x component is going to be positive, the y component is going to be negative, the angle from the horizontal is 60 degrees. So I propose that we've got actually, let me write it like this. Oh, just a tad. That's going to be my F1. Is everybody okay with that? I think by now that the description of force vectors should not be anything that's inherently complicated. I think we've done that enough that we can kind of just get through that. Sound good? All right. So if I chug this out, I'm going to get, here, I'll put it down here. So 5 times the cosine of 60 degrees, that is 2.5 I. 2.5 I minus, and this one's not as pretty. This one ends up being like 4.330 J. And remember, actually, let's just do it like this. Keep it short. This is in kips. Okay. Let me stop for a sec. Does that make sense? All right, any questions? All right. Now I want to handle this force 2 a little differently. I'm an engineer. I'm not a mathematician, which means I look for ways of doing problems as efficiently as possible, okay? So let me explain. So here is force 2. Okay, so this is force 2. This is force 1. Okay? Now let's take a look over here off to the side at force 2. All right? So we've got this slope ratio that's defined 3 to 4, and that's going to be our angle, right? So some of you are probably thinking, okay, I need to do theta 2 is inverse tangent of 4 over 3, right? And then cosine theta 2, sine theta 2, all that, right? That's what a lot of you are thinking. No, let's not do that. Instead, let's go back to basics. Let's go to Sakatoa. Let me show you something. So watch this. So F2 is going to be, so it's in the same direction. So we're going to have 5 cosine theta 2 times I plus negative 5 sine theta 2 times J. But let's use some common sense, okay? So look at our triangle here, okay? So here's our triangle. Man, I can do better at that. Maybe not. What's the hypotenuse of that triangle going to be? 5. Now, if this is our angle right here, I seem to remember that the cosine of the angle is found as the adjacent over the hypotenuse. So I think what we can do is we can say that this is just 5 times 3/5 plus -5 times. And I seem to remember that the sine is computed as the opposite over the hypotenuse. So the opposite over hypotenuse is 4/5. So this is going to be 3i minus 4j. Notice how I did that with a lot less button strokes on the calculator. You see what I mean? That if you want, you can be a mathematical purist and say, I need to take the inverse tangent to get that angle, and then I need to take the sine and cosine of that angle to get the x and y components. It's not wrong, okay? But I would argue it's harder. I would also argue that you are potentially introducing more error into the problem than actually exists because you're rounding out decimals and things like that. So I think it's easier to just use the trig functions directly. A lot of times in engineering schematics, instead of giving you the angle, you're going to be given the dimension. So for example, if you're looking at a truss, they're not going to give you the angular dimensions of each diagonal member. They're going to give you the overall dimensions of the truss, and then you have to figure out the x and y components. And I would argue it's easier to do what I just did than all of the angular calculations. Does that make sense? Again, try and make the job as easy as possible. Okay. Now, here's F3. So can somebody describe F3 for me? Well, so look at what we have here. So F1 is something times I plus something times j. F3 is something times I plus something times j. What's going to be multiplied by I for F3? 0. And for j, it's going to be -5. So F3 can be described as -5j, is what I'm saying. Does that make sense? Because it's just a vertical vector, it's pushing downward, and so F3 -5j can just be done by observation. All right, so let me scroll down a little bit so I got some room. Again, I always like to make sure that the units are written out. I know that seems repetitive, but later on, I think it's a healthy exercise. Now, for vector number 4 is going to be like this. And that's a boat pushing on the barge. So this is F4. And it's pushing to the right and up. So both the x and y components are positive, right? And so now this one's going to require a little bit of trig, especially because it's 45 degrees. If I take sine and cosine, I don't get nice, pretty decimals at the end. So it's going to be 5 times the cosine for the x component, 5 times the sine for the y component. So I said that right? Yep. So F4 All right. Okay. So 5 times the cosine of 45 degrees. I'll be nice to you this morning. I'll read you that one out. The cosine of 45 degrees is about 0.707. So 0.707 times 5 is about 3.5. You end up getting 3.536. Okay. I'm going to stop for a second, see, one, I'm going to let everybody catch up, and two, I want to see if anybody has any questions, if this makes sense. That, I needed some coffee this morning. All right. Okay. Sound good? All right. So, ultimately what we're doing is adding forces and moments. So if I wanted to add up all the forces, I can do that right now. Because I've got F1, F2, F3, F4, just add them up. But I'm going to hold that off to the end. Instead, what I want to do is I want to get to the point where I can start adding up moments. Okay? Now, in order to do moments, we're going to need an R vector and an F vector. Okay? We're going to need that for both of these. We're going to need both in order to determine moments. Now, if I scroll up here, let me scroll up here. What we're going to need is an R vector associated for every one of these forces. So we're going to need an R1, an R2, an R3, and an R4. Now, where do these R vectors start? They start at point 9. So we're going to have R1, R2, R3, R4. Let's draw these. Let's go ahead and do this. So let's start off with R1. If you had to describe R1, can you do that by just looking at it, by observation? How far do you move along the x-axis horizontally from O to that point? Say it again. 90, but not 90, negative 90. How far do you move along the y-axis? 50. So could I write R1 as negative 90i plus 50j? Pretty simple, right? So why don't we do that? Why don't we say that R1, and I apologize in advance for the scrolling. So let's say step 2 is position vectors. From point in question. So R1 is just going to be negative 90i plus 50j, and the units for that are going to be feet. Okay? Let's see if we can reason the rest of these. What about R2? Can somebody tell me what R2 is going to be? Not R2D2, just R2. Somebody thought he thought it. All right. So how would I describe vector R2? 100i plus 70j, right? What about R3? It's going to be 70j still, but how far along the x-axis from 0 to force 3? 400, right? Does that make sense? So to get from point 9 over here, so that's R3, we go 100, 200, and then another 100. So that gives us 400 feet, 400i plus 70j. And then finally, to get to R4, so that's R4. How do we get to R4? How far do we go along the X? And how far do we go along the Y? Negative 70. Okay, so if I wanted to describe these vectors, it would be as follows. It would be R2 is 100i plus 70j. R3 is 400i plus 70j. And then R4 4 is 300I minus 70J. And again, all these are in feet. So far, so good? Okay. All right. So now what we're going to do is, again, to turn this into an equivalent system, what we're going to need to do is evaluate R cross F for each force and some forces / moments. Now, I'm an engineer. You're engineers. Engineers love tables. We're going to do this in a table. Okay? So, these forces represent boats, right? So let's see. All right, let's see. There is 1, 2, 3, 4 boats. Let's write out the R vectors. So what did we get? We got negative 90I plus 50J. We got 100I plus 70J. We got 400I plus 70J. And we got 300I minus 70J. Okay. Now let's write out the F vectors, which these are in kips. And so we got, and this one I'm going to write 0I minus 5J. And this 3.536I plus 3.536J. And so now what we're going to do is we're going to compute R cross F. Now, do you remember our shorthand formula for that? How did we do that? Remember this? RxFy minus RYFX. The unit's going to be, they're going to be in foot kips. So how do we handle this? We do it row by row. So for the first row, we're going to have, whatever, that moment is R1 crossed with F1. So everybody brought out Casio FX115ES Plus or similar scientific calculators to Engineering 213 this morning, I hope. So how do we do that? Do this times this minus this times this. What do we get? So negative 90 times negative 4.33. So, I don't know, 370, 380, something like that, however much that is. And then minus, what is that? 125, about 25. So tell me what we get for this. 264.7. Do I have a second on that? Okay, good. So this is positive 264.7. Okay. So let's keep doing it. And that's what we're doing. We're computing a moment vector. Although, actually, hold on. I think my notation's a little off there because, remember, in 2 dimensions, yeah, it's a vector, but it's just something times k. Really, all that matters is the magnitude. So I shouldn't have arrows over those because they're just numbers. So what are we getting for this, and this, and this? What are we getting? So how about M2? I think I might be able to do that one in my head. So negative 400 minus 210, negative 610. Did I get that right? Okay, what about 3? So negative 2,000 minus 0. And this one I'm going to need some help with because it's going to be this times this minus that times that. I'm guessing that's going to be positive. Yeah, it's going to be positive. I think it's going to be just whatever 230 times that is. So anybody got an answer for me? $1308.32. We'll call it 1308.3. Do I have a second on that? All right. All right. So now what we're going to do, we're just going to sum these up, right? So if you've already had calculus 2, you know that big letter sigma is summation notation. I hope that bringing up calculus 2 do not start any, post-traumatic issues. You all had it with that. You're up to your limit with calculus, right? Up to your limit. Come on. We got to tell calculus jokes. They're so integral to learning. Okay. I'm such a dork. Okay. So my jokes aren't very original. They're all derivative. Okay, so I love my job. Okay, so now what we're going to do is we're going to add up all the f vectors. So what that means is add up all the x components and then add up all the y components. So for the x components, 2.5 and 3 is 5.5 to 0. 5.5 plus that. I think we're getting 9 point, we'll call it 0.4i. This one's going to be negative. I might need some help with this. What are we going to get when we add up the j components? You non-civil engineers are going to miss out on all my jokes in other classes. 9.79, is that negative or positive? Oh yeah, well I already put the negative there. So 9.79. Do I have a second? Okay. And then what about summation of the moments? By the way, I have a sum here, but we don't really care what the summation of the r vectors are. That doesn't really mean anything. What do we get when we sum our moments? It's probably going to be negative.
Negative 1,037.
Say it again. 1,037.
Yeah, negative.
I think like 0.2. What's that? 0.3. Well, I'm leaving it as 0.2. No, that's fine. I will change it. Yeah, no, that's fine. That's fine. Okay, so everybody okay on that? So what I propose is that here's what I'm proposing, okay? what I'm saying is that we can replace, how many boats did we have on this system? We had what? 4 boats. We can replace that with 2 vectors. R being 9.04I minus 9.79J in kips. And then if we want a moment vector, the moment vector would be negative 1037.3 times K. Because remember that in 2 dimensions, whenever you have 2 forces that are crossing 2 dimensions, the result rotates around the other axis, and that other axis in this case is K, and that's going to be in foot kips, okay? Now, the way that we would draw that is, and please forgive my artwork, I'm going to do my best. That's the barge. I think I did okay. I mean, here's what it looked like up here. And here's what it looks like here. That's the best you're going to get. Okay. This is 0.0 or 0.0. Okay. And what I'm going to do is instead of those 4 boats, you know, the one that was here, 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 what have you, I'm going to replace that with just 2 vectors, okay? A single vector that goes like this, all right? And that is my R vector. And then I need a moment vector, okay? Now the moment is pointing out of the screen, so the way that I'm going to handle that is I'm just going to show its rotation. So its rotation is going to be sort of like that. We'll call this the M vector. In terms of its direction, in 2D, if we just respect our Rx of Fy minus Ry of X, positive moments are counterclockwise, right? Because here's the x-axis, here's the y-axis, and so if we curl this way, positive z points like this, so our fingers are going counterclockwise, but we got a negative moment. So negative moment would be clockwise moment like that. So this is our answer for part 1. This is what I'll call answer. And I'm going to call this system 2. System 1 being this. This is system 1, the original system. And I propose that I can take system 1 and replace it with this, and it is statically equivalent. The same amount of forces, the same amount of moment. Okay? Does that make sense? Now, we're not done because we're ultimately going to derive system 3. So maybe what I'll do is I will put that here. So far, so good? Okay. Now, remind me, what was the magnitude of each of the individual boats? 5 kips? Okay. Keep that in mind. So let's go back to the original problem. Okay. So problem says 4 tugboats are each exerting a 5,000-pound or 5-kip force on the barge. Determine the equivalent force system. Done. Where should a single, more powerful tugboat push the cruise ship to produce the same effect as the original 4 tugboats? Let's start off with single, more powerful tugboat. Okay? So I want a single tugboat, and it's got to produce the same effect as the original 4 tugboats. So how do I represent that single, more powerful tugboat? Well, that single, more powerful boat better be that. what's going to be the magnitude of this resultant force? It's going to be bigger than 5, right? It's going to be, I don't know, 15, 16, whatever Pythagoras tells us it is. But imagine I have this boat. Where do I place this boat to generate the same effect? Well, I place it wherever it's going to generate the same moment. Okay? So I propose what we need to do is the boat's going to push somewhere on the top of the boat, or somewhere on the boat. I'm going to take the boat and sort of put it somewhere up here. Let's see if we can figure out where we need to place it. Okay? Let's see if we can figure that out. So I'm going to draw my boat again. Actually, yeah, I'm going to draw my boat again. Okay, there's my boat. Let's do this. Let's call this point naught. And let's take a single more powerful tugboat and let's put it somewhere up here. Now, why am I placing it there? Somewhere over here. Well, because if I place it over there, how is it going to rotate point 0? It's going to rotate point 0 like this, the same direction that that moment is rotating. That's why I'm placing it this way. Instead, I could take point R and place it over here, but then it would rotate it the opposite way. It wouldn't do what I wanted. All right? So, ultimately, what I need to figure out is what is my position vector. Okay? Now, this dimension here, I don't have a clue what that dimension is. That's kind of what I'm figuring out. We'll call that X. I don't know what that dimension is. But do I know what this dimension is? It's 700. Or sorry, not 700, 70. That dimension is 70. Okay? So what do I know? I know that R is X times I plus 70 times J. I know that my force vector is 9.04 I minus 9.79 J. And I know that my moment has got to be negative 1037.3 K, right? This is in feet. This is in kip. This is in feet kips. So, the moment is going to be Rx Fy minus Ry Fx. The moment is going to be negative 1037.3 equals X times negative 9.79 minus 70 times 9.04. So negative 1037.3 equals negative 9.79x minus 637.8. All right, that might be 632.8. I might need somebody to check me on that. Yeah, I think that's 2. So therefore, all we have to do is solve for x. Move that over here, divide both sides by 9.79, and I get x is and if you want to be clear, this is now system 3. We went from 4 boats to 2 vectors to just 1 force, to just 1 vector. And the question is, where do we put that force in order to generate the same effect? those and that is the tenet of equivalent systems. Okay? Does that make sense? All right. I think hopefully now you're starting to see like the light at the end of the tunnel with everything that we've been talking about. Okay, everybody, I'm going to pull up the QR code. That's all I've got. I will see you all on Wednesday.